Quantum networking is one of those entities, just like regular digital networking, where you know that you need it, but you don't think about having it. The moment that you start to connect quantum computers, connect quantum sensors, connect quantum networks at scale by using quantum memories, you're going to unlock an entirely new series of applications that people haven't even thought about right now. There's a lot of quantum that still lives in the space of a deck and a dream, right? so, so, so we're proud of the fact that we produce something. So I would argue we probably have put more quantum hardware into the actual hands of customers than any other quantum company at this point. You have to invent the tech and you have to invent the market. It's amazing how much the availability of funding has influenced the expectation of innovation. I think we've barely scratched the surface. The reason quantum compute has started talking about its impact on materials is because quantum computers are effectively quantum materials, right? So they're very good at emulating and solving problems about other quantum materials. And I mean, it's abstraction, right? But I think that this is something that will have impact on the world in ways that it's true. We don't know what that means right now.
Welcome to the Quantum Economy Podcast. Today we take a closer look at quantum from an infrastructure perspective. My guest is Noel Goddard, the CEO of Qunnect, a company building hardware for quantum networks and bringing quantum communication onto existing telecom infrastructure. We explore how quantum networks are being shaped and how today already Qunnect is sending entangled photons through Brooklyn and Queens. We look at security, scalability, and also the practical challenges behind building quantum infrastructure. Thank you so much for tuning in. Feel free to subscribe and like. And here's my conversation and the Quantum Economy Podcast with Noel Goddard.
Noel, first of all, thank you for doing this. And I've done a lot of conversation lately on quantum technologies where we talked about the computing story. But I ran across your work and you kind of sort of look at it from a networking perspective. And I would just be curious, why you think quantum is more about the infrastructural part of things? And maybe also you can explain a little bit about what quantum networking is all about.
So thanks for having me on your show, which is great. I think quantum networking is one of those entities, just like regular digital networking, where you know that you need it, but you don't think about having it. And I think that's true also in the quantum space. So at the beginning, everyone was talking about quantum compute. And of course, this received a huge amount of attention on the investment side, but also on the development side, because building brand new types of compute and processors, right, is a wildly expensive hardware proposition. But on the side, there were these two other verticals, quantum sensing and quantum networking, that did not receive the same amount of sort of attention in the early years. Now, quantum sensing has become really interesting and attractive because you're starting to understand that in GPS-denied environments, we need a different way to start thinking about how to register, landmarks, etc. But in the background of that, right, you have this quantum networking piece where, again, I think Europe has been largely thinking about quantum networking as a way to distribute keys from some of the initiatives that they've had there. Mm-hmm. But quantum networking has a second very clear purpose, and that's this idea of quantum channels connecting quantum things, right? And if we think about the internet and the power that allows us to be able to actually record live on a podcast, right, across countries, right? Those types of technologies were not things that were even imagined in the 70s of the digital internet. Yeah. But quantum networking has the same sort of promise. You have to actually think about the fact that the moment that you start to connect quantum computers, connect quantum sensors, connect quantum networks at scale by using quantum memories, you're going to unlock an entirely new series of applications that people haven't even thought about right now. So in 1970, people weren't thinking about streaming video over, the early days of the ARPANET. So similarly, I'm sure that there are going to be things that we're not thinking about today. The more near-term applications of quantum networking are, I think, the use of quantum entanglement, which is really the information currency of quantum networking. So the use of that in order to enhance security of existing digital networks. And then the longer term vision is how do you create the hardware that both does the security aspects today, but then serves as a generalizable infrastructure tomorrow.
Hmm.
And I think that gets at this idea of we all compute through data centers, whether we know it or not. But within the data centers, there's tens of kilometers of fiber. It's literally like a city's worth of fiber and those types of interconnectivities and networks and meshes that are squeezed into a building. And that's not trivial to be able to operate if everything needs to be quantum, and you have to learn how to route that quantum information. You have to learn to interface it with the devices. But that's how our world works right now. So I think that's where the larger infrastructure play is. And it's an important piece of the quantum compute story as well, because quantum compute has a hard time putting more qubits in a single processor. But
Hmm.
if you can network those processors, you can gain the power of that connected overall device. And we look to service both at Qunnect. So basically, we build solutions which aspire to be generalized hardware infrastructure, but have near-term applications in the security space.
I want to get back to the entanglement part and also Qunnect, what you guys do, but also I mean, we could say that a quantum computer would always be a special purpose computer, and as conventional CPUs, GPUs scale, you get more energy efficiency, and how would you like describe the main differences between a classical information network and a quantum network? Like just from a like a layman's term way of looking at how would a network be different to a classical conventional compute network?
So quantum computers use quantum information, so for instance, entanglement, in order to compute. But you can't transmit your entanglement across a classical fiber channel. So what the digital network is today is a bunch of digital computers and digital devices connected by digital channels. That digital channel doesn't carry your quantum information.
Hmm.
So in order to be able to create something which actually connects those two quantum computers in a way that's useful, you need a quantum channel in between to carry the quantum information to interface it with the quantum devices. That's at its most rudimentary. But if we think about what quantum information is, so first days of the internet, the world was still wired with copper, right? All of the data that was transmitted, whether it be via taking your voice over telephone, or in the earliest days of packet switching that ended up being the roots of the current internet, those were electrical signals distributed through copper wire.
Mm.
Then, fast forward sometime later when optical fibers started to become routine, and they were a type of infrastructure that was being built everywhere across the US, Europe, etc. Then the currency of information went from being electrical signals and copper wire to being optical signals and optical fibers. So those optical signals today have, hundreds of trillions of photons in them per burst. Quantum information uses those same fibers, but actually now those fibers are going to carry that quantum information as single particles of light. But the information is very special because the information that we use is entanglement. And entanglement, when it's created, basically is created as pairs of particles of light. And the relationship between that pair in terms of information is defined by the physics that created it. And what's nice about that is that that's nature. So what you're doing is you're using nature's sort of guarantee that what you create is this perfect thing. And because you have a pair, now you can always use the second half of that pair as a check bit for any type of security protocol that you would like to validate, because you know what it was when it was created. If it's been corrupted, then you have to understand, was the corruption something that happened because of some craziness in the environment, or was it because you had a hacker, etc. So that's why the security aspects of quantum networking, I think, have been very forward, because that's a natural place where now it can provide something that enhances something beyond what digital can do today. but the long-term goal is to support this idea of being able to create literally a quantum network that transacts quantum information between quantum devices.
We could argue that these are still, because I was referring to the special purpose. I mean, obviously, we need QKDs and some kind of security layer that tackles, post quantum cryptography. But I was curious to understand, if you look at the use cases. Obviously, there is, in a quantum world, you could argue, obviously, this is an approach to take, but we still, at least from a quantum computing, and I would always argue that, like, from a business use case, people are looking at, from an investment standpoint, what are the actual business use cases. So when you go ahead and I like this, by the way, to send entangled photons to Brooklyn and Queens. I mean, it's the the most like funky way to put out a marketing statement to do. I'm going to do entangled photons through Queens and Brooklyn. What does that even mean in practice?
Yeah, and like normal application space, right?
Yes.
So yeah, it is fun, right? So the marketing side of quantum is fun because, of course, it plays always at the edge of science fiction, and I think
I
we
call
all
it,
have it.
by the way, it's not science fiction, because anything we want to imagine today, we can actually apply. So my co-author and I refer to it as sci-fi, PHI, science.
Oh, nice.
Different. But
Yes,
yeah.
yeah. So, but it's. I think first off, you're sort of definitely going towards what it is that we like the best about our tech. We were very determined from the early days to deploy this stuff on real fiber and take it for a test drive. And so when we raised our first Series A round, it basically supported taking things that we had in very early prototype stage, bringing all of those devices to market, which is now our full stack. And that full stack supports the distribution, preservation, and validation of entanglement on standard telecom fiber. So we went to fiber carriers in New York and we said, we'd like to rent some fiber to be able to test drive our stuff. And they're like, what are you going to do with it? Then go through this entire... Exactly. Can you cut us a discount because we don't know what we're doing type of moment? May not work. But so what's fun about it is that it is the fiber that was there already. Nothing was laid especially for Qunnect.
Right.
They took existing fiber that in all these fiber cables, put together some paths that we were able to connect some instrumentation at either end. And we turned on the device, right, at various locations, and we started to broadcast entangled photons through these fibers between these locations. It was certainly a cross your fingers moment for us. We had no idea that it would work as well as it did, and we've certainly optimized it over the years. But what we're really good at right now is being able to create extremely high purity, high quality entanglement at the sender side, distribute it to the receiver, preserve it during transit with these things that act a little bit like noise canceling headphones on the fiber. And then at the other side, where you have the validation hardware, you can start building these protocols. So when we first did this in New York, the first sort of public release of the data that we came and the performance metrics came out in 2024. Deutsche Telekom got very interested in it, and they were shocked that you could run these things 24/7 operation, 99% network uptime, weeks at a time operation. All of that started to look like real world networks as opposed to academic proof of concept. And they asked if they could install our equipment on their network in Berlin. It turned out to be extremely exciting to us to have a partner who obviously is a network operator. And they proved out that not only they could replicate our results, but actually they did better than we did because you have better fiber in Europe than in New York. And I think the other really exciting piece is that on the same fibers themselves, they were carrying digital data traffic. So the way that we've always felt like quantum would evolve is that it first has to provide benefits to the existing digital. So you would always have it in a hybrid type of context. And when you bring that benefit, right, then you start to be able to address what would you do with a use case. So Deutsche Telekom showed that they could distribute over all of these multiple paths that they were choosing in their network, all of which they could stabilize in different ways to show that they could reach high fidelity performance. And then they did so in the background of this data traffic. Then both they and us and many others now have shown that Qunnect's equipment can broadcast this entanglement and validate it. The trick next is to say, how do you use it on the ends, right? So we have two recent works, one with Cisco and one with Deutsche Telekom, where we showed that you can now manipulate and transact that entanglement in ways that underlie what people plan to do to be able to entangle two quantum computers or two quantum memories or two quantum sensors, or having those quantum computers interact with the network itself. So while it seems like these are baby steps, they're actually huge research leaps. And the most important part, at least as far as we're concerned, is that we showed that you could do it with a purely commercial hardware stack. This is not some sort of mostly research laboratory tied into something that's partially commercial that then ends up being advertised as, the next product. These are full stack solutions that are talking to each other and doing these interesting transactions. So super proud of the fact that it worked. So the Manhattan Brooklyn piece, which is funny, is that we not only have broadcast entanglement between Brooklyn and Manhattan, but we've also now shown that we can do this type of very cool physics thing, which is a candidate protocol for data centers and other types of complex networks, where basically you take two racks, both broadcasting entanglement separately, where one half of the entangled pairs go to a centralized hub in between. And when those are transacted at the hub, you actually pass the entanglement or share the entanglement with the two remaining halves of the photons that remain. So this is called entanglement swapping. It's the candidate protocol for being able to entangle two computers. So if those broadcasters were broadcasting to computers at the edges and a hub in the center, you would be able to link the two computers on either side. And yeah, super exciting to see that it worked as well as it did.
Yeah, it's really interesting. I mean, obviously, very interesting to see how that pans out before even we have stable quantum computers. But what would you describe as a technical challenge? What are the hardest technical problems when it comes to sending the quantum information through the quote unquote real fiber or the classical fiber? When you say we have better fiber in Europe, what are the technical challenges when you have that approach?
So you have better fiber in Europe because it's routinely upgraded and also probably went in later than some of the original fiber in New York. We work on fiber strands that are 20 plus years old in some of those
From a
segments.
communication standpoint, I would argue,
Yeah.
I live in Germany, and you can have a 99%, high fiber network integrated into the ecosystem throughout Germany, and you still don't even have internet connection or phone accessibility. Even though there are 20 million people living in a small spot,
I
there
get
are
it.
no mountains, no disturbance. So, I mean, you mentioned Deutsche Telekom, which is probably in the future going to be a distribution channel, a sales channel for Starlink or some satellite communication. So,
Probably.
I mean, yeah. So basically,
It's-
I'm just curious about what are your
What are the tech challenges, right? I mean, I think so at the base, whether it be Europe or the US, fiber is just a piece of glass, and glass is a material. And when you try to send light through that material, the material itself can corrupt. So now you start talking about sending single particles of light through that material, and any parts of the material which are inhomogeneous, etc., right, will react differently to the light that's being sent through it. What's crazy about fiber is that because, again, it's a material, it reacts to vibrations which are near it. It reacts to temperature changes. So in the US, we have aerial fiber as opposed to berry fiber in a lot of places in rural America. And that means that these things are swinging in the wind. Sometimes they're wrapped around power cables that have external fields. So learning to correct for all of these environmental disturbances in a way that creates a stable channel where you can send this information was literally spawned the creation of an instrument, which is one of our most popular instruments for quantum networking in general, which continuously tests the channel you're trying to broadcast through, that fiber, for the real-time conditions, and then creates this compensation signal in order to be able to compensate for what the real-time problems are. When Deutsche Telekom did their demonstration with our technology, they literally used a switching technology to switch between different lines in their network. Each time would be basically tested and compensated for so that they would get the optimal conditions for broadcasting in each one of the fibers. And it's very fast. It's in an automated way. So I think correcting for the real world, that's always one piece. That was hard. Performing these transactions actually plays to an early design decision that we made when we were creating the stack. And that was to create our entangled photon pairs in a way that's different than what others use. So most of the entanglement sources on the market use lasers to pump a crystal, and then the crystal gives off these pairs of photons. We actually use lasers to pump a cylinder of atoms. And unlike a crystal where there's sort of naturally defects just by the fact that the crystal is a material, instead, you have atoms, and they're one of the most perfect things in the universe. So that means that the types of photons that you're creating are highly identical because they're being created from these things that they're interacting with, which are absolutely identical by nature. And that means that we have a high purity source, but also the special part about it is that since there's not the sort of secondary problems you have with light scattering through crystals, you also have very narrow line width photons that are the output. Why that's important is that spectral shape of the photon needs to match whatever you're interfacing with. So quantum computers and quantum sensors, all of these devices have line width requirements, which are sub-gigahertz. Our source is also naturally sub-gigahertz. But by contrast, all of the other entanglement sources which are out there are terahertz or above. And that mismatch in line width comes out as just pure loss at an interface. And you can imagine in a network, if you have lots of these interfaces just compounded across the network. So for us, when we were thinking about how to build a network in terms of these challenges, we wanted to use polarization qubits because that's what quantum devices use. Polarization is affected by going through fibers, so we needed to learn to correct for it. And then we also needed on the other side, right, to think about how these things would actually interface with another device. So to minimize interfacial losses. It turns out that the use of those narrow line width photons is also good for fiber transit because they're not dispersed throughout the fiber in a sort of long segment so that you can correct more easily. So all of these were fundamental design decisions in the early days, but it had to do with creating really high quality entanglement at the beginning and then preserving it really well in transit.
When you do so, I mean, you anticipate a different economy, a different structure. I mean, when you buy a Qunnect system today, is it a product? Is it a research project, or is it a different strategic option on how to build the future? I mean, obviously with Deutsche Telekom, they have their very classical structures of how to communicate. And when I listen to you anticipate a completely different world of communication and also how we operate on a business level. So when you say like you get clients today from Qunnect, what is it? Is it a product? Is it a research, like an option of the future? Is it actually a very clear vision for you to see that this is how we will operate in the future?
It's a great question. So we're particularly proud of the fact that we have real products. There's a lot of quantum that still lives in the space of a deck and a dream, right? So we're proud of the fact that we produce something. So I would argue we probably have put more quantum hardware into the actual hands of customers than any other quantum company at this point. But the deeper part of your question is how far away is this from a customer who is completely quantum naive being able to use it in the networking space? And
Exactly. Are we preparing
yeah.
for a quantum network that is coming? Is it inevitable? I mean, basically that's what I'm aiming for. Yeah.
I think the quantum technologies, which you're seeing very clearly in the quantum compute space. So quantum computers were supposed to solve all problems, and everybody was very excited. And then they started year by year admitting to some of the big challenges, and each year it's a different story.
Yeah.
But they just got this boost because they all went hybrid with NVIDIA. And I think that that's actually the same answers for all of quantum technologies, because it turns out that our digital world is very sophisticated. So to have a value proposition within that space to outperform in some way is tough. But if you can show that you significantly enhance something by adding quantum to it in a hybrid structure, that is a value within itself. And compute is taking that on right now with NVIDIA primarily. I think that we are doing it by showing that there are applications that can be added basically as physical layer security on top of existing digital network traffic. The United States has a program funded by DARPA,
Mhm.
which is called Quantum Augmented Networks, abbreviated Qunnect. It specifically started off with regular digital networking and asking how quantum can augment that. And I think that's how we view our products as well. This first generation of products, the racks we sell today, so the product we sell today, yes, that is a rack intended to support discovery. But the market today is small networks with first hardware, whether they sit in industry, like in the case of Deutsche Telekom, or they sit in government, like in the cases of many different government agencies and states and other things, or in academic centers. And sometimes, of course, there's a mix of all of those things. So that's just where the market is today. But I think that if you look back to how ARPANET started in the US, it was first hardware on first small networks, open to the next generation of people who would build the middleware or the application layer on top of that hardware.
Mhm.
I think that is where we are, which would have been an equivalent of the 70s in digital technology. So we need to empower that, because that, to us, is today's customer. Where we see this is you have to have some application that justifies miniaturization, industry hardening, etc. Security always offers that, because if you have true security threat, you have motivation in order to fund the development of that security application space. We are using that as a company and saying we are working with design partners today. So obviously we've mentioned only Deutsche Telekom and Cisco. We as a company also work with JP Morgan. We work with the government agencies through some firewalled exercise in the United States. All of this is to develop technologies which are going to be security products in Qunnect's future product suite, which is effectively the application that pays for the advancement of the technology into sort of like quantum inside, where everything is software interfaced in a way that the user does not need to have quantum knowledge in order to run the application. And I think we're one generation away, right? We're literally, at this point, we have products that we know work. We know that they're stable. We know that they're reproducible. We can put them on trucks and ship them places, right? So we have all of these things that we know that work today, but it's not something that I can just hand to a naive network engineer and say, if you just plug this in, it's going to run the security protocol. And that's, largely just something of upgrading the software significantly, because you have to build that application layer, and then some of the hardware to meet with that in terms of industry hardening. So as a
Yeah, I mean, I
company,
think our part is growing, right? So I mean, I would be just curious how you see the first real commercial use. I mean, security is always like the very simple, low hanging fruit to say that like we need to move into security, but like, is it quantum data center, distributed computing? Is it the quantum sensing? Where do you see the real commercial impact also for you as like the first real commercial impact on this?
so we've taken a little bit of a different tactic than the European market. So the European market, because of the centralized support of quantum key distribution, you've seen the development of entanglement-based technologies for that. And I think that's great. So there's a number of good companies in that space that are operating in Europe right now. America has not traditionally been very supportive of the QKD efforts because of there's random parts to the history there which we could dive into or not.
It changed a little bit though, didn't it? I mean, like with the efforts and also in Colorado and some of the companies that have emerged in the security space, hasn't it been a little bit more open to it right now? Or
So the U.S. has decided to jump in full force on post-quantum cryptography algorithms. There's a sort of lengthy history of how NIST, our agency for standards, was involved in selecting the finalists of this competition for post-quantum algorithms. Um, the recommendation of our government has been that we would adopt that first, which I think is still a very reasonable path, because I think it would be naive to think that people are not trying to break RSA and ECC today.
agreed.
And the moment that they're empowered with enough compute power to do it, it will happen. So we're all just kind of living on this borrowed time, but that always feels like an existential threat until it happens.
Mm.
But I think the reality is that we have to have something beyond PQC, because if we convert our entire encryption infrastructure, everything we do, Zoom meetings, financial transactions, Amazon shopping, all of this, right, lives in the RSA space. If that all becomes PQC, and then PQC is already broken, which nobody knows, what's next? And I don't like to be one of those doomsday people, but I think we just live in a world where thinking about defense in depth is an intelligent way to approach problems. Quantum networking, so QKD in particular, offers quantum computer proof keys, right? So the idea of having physical encryption for key distribution is smart, because it is truly resistant as opposed to resilient to the quantum compute hack. However, right, that's just one of many things you can do with entangled bits. What we've been working on are security protocols that enhance digital protection by turning the network basically into a sensor. So if you can distribute entanglement really well, then you can basically create this sensitive mesh to not use the entangled bits for the information themselves, but to use them as a sensor for sensing eavesdroppers. And harvest now, decrypt later attacks have been something that's been ongoing for years now, with very little way to detect them in the background. And learning how to do that better is an important part of an overall cybersecurity strategy. So you can think of it like a quantum alarm. Now, numerous other industry players like Cisco, they're advertising this also as a next first step. The other thing, which is rather exciting, and NIST in the United States just has a very good paper on it that came out in the last few weeks, is this idea of being able to provide an authentication protocol which is purely quantum. And that not only is authentication, but also position verification. So you can use the properties of entanglement. So effectively, two verifiers send quantum information to a cooperative transaction partner who provides a quantum test of that information and sends back the result. The timestamp of the transits, which is hyper accurate because of the entangled information, plus the results of that test authenticate the transaction partner. And in that case, I think that you're basically seeing for the first time like a way to do position verification of things for financial transactions. It's funny, we were recently talking to people who were concerned about identifying different types of electronics and other things that were in various locations that you could do via also these types of quantum tests to understand where these exist in space. So I think those types of applications, which had understood benefit over the existing digital technology, and there is no equivalent in the digital space, will be the first useful applications. Because the problem with the latter vision, this idea of quantum data centers, etc., that hinges also on the development of quantum computers. So quantum computers, the interface of the computers to the network itself, and the network architecture all need to be in place in order for the power of that to be realized. I think what's super exciting is that the same hardware we're building today for the security solution will support the latter. What you're talking about doing is effectively adding quantum memory to the stack, and Qunnect was the first company globally to commercialize a quantum memory 2021. So we're certainly hoping to be part of that dialogue.
Well, you joined Qunnect before that, but after the funding of or foundations of the company, would you consider yourself a startup today? And also, I mean, if you look at the
Yes.
Google and the Amazons and the scale ups, I mean, the hyperscaler, how is this race going to pan out? Now you're doing a Series B, and you're raising money to scale. Maybe we can elaborate a little bit on this journey, but also you're still small in in comparison to these hyperscalers. And I was just fascinated by like you joining a quote unquote lab experience and taking it to a real commercial organization. So just, I mean, elaborate a little bit on where you are, how you see yourself in the market, and also how you're going to compete against these hyperscalers in this very, very, I would say capital intensive journey that
Hardware
we are.
race.
Yeah.
Right. No, I was only laughing because in software, nobody thinks that it's strange, right? In
Yeah.
hardware, it's strange because of the capital intensive nature, right? So whenever you talk about people challenging the hyperscalers in the software space, nobody blinks an eye.
Right.
So I like technologies that are not an iterative step, right? They're truly a different way to think and approach problems. And when I was working with the seed fund that helped Qunnect raise their first debt note in 2019, so it's been a while ago. One of the things that I really liked about the value proposition of the original scientific founders is to think about the fact that quantum tech was, at that time, I think, doomed in the scaling discussions because almost every technology required a freezer that was $1.5 million next to it for any type of functionality. Now, quantum computers, because of the intricacies and obviously complexities of those, they can sit in a room. They can have tons of PhDs taking care of them all the time. So our use of compute as a world is largely cloud-based now. So this idea of interacting with the exquisite thing from a distance is not something that's strange to people. They don't all need on-prem. But quantum networking was different, right? Because networking is different. You have hardware and normal networks distributed like every 25 kilometers for repeater nodes and other things. There was no version of that was going to support the idea of having these exquisitely finicky and expensive freezer units right along the way. And Qunnect had this room temperature memory technology. I thought it was extremely exciting that anything could be done well at room temperature for quantum. And it's not room temperature asterisk, right? So a lot of people will say room temperature because things are sitting in a room. Other people will say room temperature, without telling you about the vacuum requirements, right? So there are a lot of little footnotes and asterisks in the sort of world of quantum advertisement. But this is a truly room temperature tech. Literally, it sits in a box, right? And when we developed the first one, it was so rewarding to see how well it worked, and then we could get it to a point of again commercializing it and having customers. And it's still an exquisitely complicated device, but it works. I like the idea of thinking about how each part of our technology stack is optimized to think about the downstream possibilities of a real network as opposed to a lot of laboratory startups where there is a sort of archival knowledge of how to do things because this is how it was always done in order to achieve these results. And then you get stuck in this sort of pipeline of just trying to make the engineering work on a tech that was proved out in the lab. We've had somewhat of an advantage of being able to say, this is the collection of things which exist in the academic literature, and we would like to obviously use those as a springboard to where we're going. But if we wanted to design the perfect element in the stack to do this, how would we take what is understood as art of the possible and then engineer it in a way that allows us to actually achieve the performances that we would need for a real network? That part has been really fun. And I think that's what, I mean, there's a lot of research before we get to the engineering, and then the engineering is hard too, right? But I think that is how every quantum company operates. You have a huge research backend. But ours has always been fixated on this idea of deployment as opposed to just, check the box. And it's what gets all of us excited when we see this stuff in the wild, right? The first time we sold a rack and saw that it worked and obviously celebrated all of that happening really felt great, right? That it's not just in our hands, it's in the hands of a user. And obviously you learn a lot when all of this happens. But my motivation in doing this is I really love to see interesting, again, non-iterative changes, right? So this is really a significant step away from anything that was there before, but see it as a cohesive vision coming together in order to build a useful tech. The popular thing in the VC world is, did you build a solution that's looking for a problem? A lot of quantum kind of sits in that uncomfortable space, but it's also because a lot of the users don't know what quantum can do for them. And as we've started to have more quantum out in the wild, more of our tech installed in different places, it's been very fun to see how those groups like Deutsche Telekom start to use these things in a way that is with application focus, right? They didn't want to invent the hardware. They wanted to see what the hardware could do, right? And we're finally having those discussions, so that's fun after a few years of blood, sweat, and tears to get the hardware out, right?
Yeah, man, I obviously love the Brooklyn Queens narrative.
The story. Yeah.
I mean, and you've said this many times that Qunnect basically builds hardware, not the hype. But then again, it's throwing money at it. I mean, it's basically the narrative to attract investments. And where do you draw the line between like the vision and the hype? And we are in a very state where billions of dollars are thrown into the industry, and it's all about generating that narrative, right? So where do you draw the line between the future, the vision, and the hype?
So I apologize because I didn't address the hyperscaler issue, but it ties into this question. The quantum computing story has been very interesting in the United States because so many hyperscalers jumped on it very quickly. And then this mechanism of SPACing, which was not necessarily something that the Wall Street world rewarded for any other industry, seems to have become the thing that quantum does in order to...
Yes, how it's going to package 2026. That's the new thing, right? Yeah.
It is. It's absolutely a mechanism. So it's interesting to see that this ended up being a validated mechanism for the public market to be involved in weirdly emerging tech that makes none of the normal economics that anybody would consider on the public marketplace. So to me, it always feels like it's like a really advanced version of Indiegogo, right? So I think the way that we compete, and this goes back to the how do you even think about where the company will be, and how do you think about how it grows and other things. I like to think of it as the fact that eventually all of that bluster has to prove that something works. Otherwise, the market will collapse, which of course is bad for all of us. But in the background, it's like there's only so long you can continue to just put out the messaging with absolutely nothing behind it. I find it... I may not have paid as much attention to it when software vaporware was a thing. So there was a time when different software companies in the hyperscaler world would announce features and other things that were just vaporware because it wasn't real underneath. And it feels like there is something like that to the press news cycle, and that's just a function of the world that we live in. You can't live without a PR and strategic communications piece. We used to laugh that we were sort of unintentionally stealth because we had not invested in the marketing side of our world. And still, compared to hyperscalers, right, haven't invested anything even remotely near what people do for that side of it. But what you see often is the echo effect across hyperscalers, that when one has an announcement, they all have an announcement. I would urge your listeners and everyone to, every time you see one of these announcements, to look for where the report of the numbers and the performance specs and other things actually are.
Mm.
It's just like looking for the sort of source when you're looking for fake news. We should all become careful listeners to propaganda and other things by wanting to know the source of where these things come from, because there's so much out there right now that that's just a function of where society is. It is no different in the technology development space. So very oftentimes people will have strategic announcements. There is no accountability on whether that's true for the source or not, particularly if you're a hyperscaler and you have the opportunity to basically make these announcements and say, I can't talk to you about anything else because it's proprietary, right? So startups are held to a different standard. I think if we don't report, then our investors will want to know where all of this magical information is coming from. With that being said, there's certainly plenty of startups who also just advertise well above what they've reported.
Mm.
We want our technology to be used. So the way that we compete with hyperscalers is to continuously go out there and tell people that if you would like to invest in someone who advertises they can do this, but nobody's ever seen a unit produced, then that's your choice. If you would like to invest in us, and we will give you a unit in exchange for the money which you give us, we're happy to do that, and you will get something that you can use. And I think it's just a contest of whether people like to invest in the vision or whether they prefer to invest in the concrete item. With that being said, consolidation is happening across the industry. And
Right.
that's typically the hyperscaler story, right? They're hyperscalers also because they consume.
Yeah, no, I think that's inevitable. I mean, and that I was thinking about this from an investor standpoint. You just fuel any startup because it's going to get bought anyways. It's going to consolidate. The
Yes.
hyperscaler is going to buy them and just have good teams. And the fear of missing out on some new breakthrough on some IP is just like a very, very simple. Like, can you spin out of the labs? Can you spin out of the universities? Can you raise a Series A and then exit with like a good valuation? I think it's a very, very like opportunistic way to look at it from an investor. But what would you say would be like the most misleading narrative in quantum right now when you look at the hyperscalers or the whole communication? Is there like a thing that bugs you, or that you see that this is something that is very, very obvious to you, that it's a misleading narrative on how we communicate or how things are proceeding in the quantum field?
I think the quantum compute hyperscalers have lived for a very long time on advertising what they can do that will be to solve a useful problem. And they have a tendency to advertise it in the drug therapeutic space, in the clean energy / battery design space, in the logistics space. These are all areas in which investment has obviously pushed a lot of money into very interesting startup companies, which get consumed by these things as well. But it's sort of like referring to an old playbook of these are all the industries that all of the VC and others get excited about. So of course, if quantum is going to do something important in that space, it has to be better because it's quantum, right? I think it grinds us a bit when we're constantly looking at the fact that quantum compute gets away with this ability to advertise utility when they haven't solved a lot of the basic steps and problems to get to a meaningful exercise in terms of like problem solving. And the public doesn't have the sort of literacy in the field, so the scientific literacy, to be able to cut through the noise. So it's not really on the public. It's not the public's fault. And science writers, of course, are very guilty of wanting to hype things in order to get a lot of hits on their articles, right? So they're a part of the hype cycle themselves. But I think that the thing that probably bothers me the most is the difference at where quantum compute companies advertise utility to keep people excited, and the actual level of where the technology is today, which of course is very blurred, right? They rarely advertise openly. I will say a company we all admire and we think has done a very good job at advertising like their actual performance data, right, of those hyperscalers is Honeywell Quantinuum. right? I think they've been very open about always sharing what lies beneath. Some of the other yes, but a lot of other hyperscalers, I think it's known now, right, that Quantinuum has advertised that they're going to do an IPO, but um, again, it goes back to like what's under the hood, right? It's one thing to look at the beautiful chassis of a car, right? It's another thing to see what's beneath it that's actually powering these things. Quantinuum and a few others have been good about advertising that piece, and I think in making their real progress known. I'm kind of leery of the idea of like take one of everything, put it together, too big to fail type of approach, which also happens in the quantum space. All of these technologies are complicated within their own right, and simply having a portfolio of them doesn't necessarily mean it equals the same as, again, utility and function or cohesive added power synergies. So I think that's another, well, not surprisingly, because quantum itself is kind of sexy, right? That it's like prone to induce hype because people are constantly looking for kind of the mystical interface to the actual, and everybody hopes for great potential. So I think there's a little bit of like wanting to be fooled, right? The public has a tendency to want to be inspired by these stories as well. But very often with almost every economy of emerging tech, you have two big problems. You have to invent the tech and you have to invent the market, because typically the market is not educated enough on the utility of what this is good for to be able to show true market pull. And that's the difference between creating technologies which are like iterative improvements where a market already exists and you're fixing like a problem or a pain point within that market. That's to some extent easier because you can always point to what downstream market is opened and enabled by you fixing this thing. Quantum is like a completely new market that you now have to educate an existing non-quantum intake market on what they could use in order to do these things. And that's, I think, where quantum compute finds it easy to just talk about all of these existing hard marketplaces, have hard problems that they can't solve easily. So naturally, if they have a quantum computer, they'll solve it better, faster, etc. And that's not necessarily real right now. It is
Yeah,
aspirational.
but are we getting the timeline wrong then? I mean, I like when I listen to you, you're like 1993, 1994 internet. We have like the emergence, then follows tech.com and Pirate Bay and what have you not. And then
Yes,
we eventually evolves into Spotify and streaming and
it's like
Netflix and what have
cat
you not.
videos.
So yeah, exactly. But so you when I listen to you now, I would like kind of sort of see that you're looking at a much longer timeline, 10, 20 years to have an adoption. And the first question would be, is that your view of how it evolves? And also, if that is so, how would you build a venture-backed company on top of such a reality?
Well, I definitely think what you're playing to is like what you actually are observing in the marketplace of quantum compute. Quantum compute was exceptionally exciting to venture capitalists in the beginning. There were a lot of entities that can say they were in the early days of PsiQuantum or they're in the early days of Cambridge Quantum, et cetera. There are a lot of investors that were there at the beginning, and some have fared well because of the SPACs that we were talking about. But if you actually look at how those hardware companies have transitioned their own developmental cycles, very often, and it was taking in venture capital at the beginning, opening up opportunities, seeing the pathway was going to be long and expensive, but the primary customer was not going to be a drug company or a battery company or any of these. That while it was interesting, a lot of the sort of pilots showing quantum compute utility were just that, right? It was sort of one and done because it's interesting to model maybe a basic molecule or an interaction of water with something. All of that's interesting, but it wasn't something that people were dipping back in and saying we need a lot of. because at the current state of quantum compute, they just simply didn't have the power, right, or enough qubits in order to solve more ambitious problems. So then they were like, how are we going to fund this? And that has been a combination story of leaning back into the government, which is also rational because it is a sovereign capability, which is why you're seeing governments supporting that role, right? And then other growth funds stepping in and deciding whether they want to be a part of that story, largely in the sort of investment bank side, et cetera, of wanting to bring these things to SPAC, right? And I think with that amount of cash now in the system, you're seeing entities that SPAC'd years earlier now reaching back into the public markets in order to capitalize their growth because they don't need to reach into government, or they do some combination of both. All of that has been a different way of building an incredibly sophisticated, expensive development timeline technology. So I think quantum compute is a long horizon game, period. Quantum networking, by contrast, is here today. These things are deployed. We've done it. We're growing in customer base. I think the technical risk of going from something that is it's operating today in the hands of users that have, they're quantum savvy, working with networking engineers, as opposed to completely quantum naive network engineers. That's just a technical step, right? That's not like a deep science step. That's the type of thing that is a low technical risk hurdle. So Qunnect to go from what we have today into going into something that's sort of industry hardened, miniaturized, improved margins, all of the things that you would go through in a normal technology company for hardware. That's not a high risk game. That's a matter of investment into it and accessibility of people to buy it for the price point. So that to me feels like we're at a very different stage of reality and adoption. So you're going to start to see in our own space, right? We certainly are going to see increased adoption over the next 2 to 3 years, which are driving application design of the rack that we do today. But we're also raising capital in order to fund that other effort, right? So the other effort is to create the security product suite, because those are turnkey application-specific things that quantum naive users can find value in today. And then the other thing is to take the same units that we have, begin to miniaturize, and to start caring about the manufacturing piece of this as a way to increase the profit margin and make it more like a real hardware company. A lot of times when people, you know this well too, I'm sure, but there's a reason everybody invests in software, not just in the quantum space, right? But just in general across the investment space. Hardware in general has been something that has been a difficult thing to back, because you're constantly looking at this market, manufacturability, distribution, all of the things which make hardware a much more difficult investment strategy. And you see a lot of deep tech funds, some of them will just say at the beginning, we don't do hardware. So it has been interesting, in at least in our journey, right, that we finally can say that we're out of this place where there's a huge amount of research risk in developing like things that had never been done before, and turning it into very measurable technical risk, which is not an unfeasible thing in order to be easily adopted or broader adopted.
Well, we connected the internet through sharing information, exchange of information. We built softwares and apps on top of that to interact. We look at quantum networks and exchanging information in quantum states. Do we need to think about information as such in a completely different way? I mean, obviously, with AI and algorithms and more compute, we can generate, on device a lot of these things. So I mean, the interaction, watching a movie, whatever. But even to that extent of solving problems, so like you have the interaction of humanoid robots with a physical, quote unquote, reality that we relate to, learning patterns, the compute, the energy. There is a completely different way to look at reality. And I wonder if we have to rethink how we look at the whole interaction of information itself when we go 10, 20 years down the road.
I think that's fair. And when you're asking me about the long horizons,
we're diving into some philosophical
No, but I
implications.
think it plays into, I mean, like, how do we think about, it's amazing how much the availability of funding has influenced the expectation of innovation. So the idea that the VC timeline became the innovation cycle, right? I mean, the two are highly matched. Um, I I think again that the good analogy of the basic internet is that when people started inventing packet switching, there was no idea this was going to be able to carry the type of bandwidth data that we have today, right? But by by creating a standard on the early years that people could start making engineering improvements to, that has really been the story of the few decades of advancements. Uh, I don't think that it would take, just because we've learned to treat information differently now. Uh, I even think back to like the first cell phones, right? And how often they dropped calls and you would like be missing different syllables and all these other things. But you think of the algorithmic improvements that learned to patch those together, so that we started having seamless cell phone calls, right? That was really because somebody brought a standard to bear, and because then the problem started to be the iterative improvements of something which we have understood pain points. But also because you have a sort of a level platform that comes up, you're starting to think about how can I use the information differently. And I think data streaming for video streaming, et cetera, right, is exactly that problem. Think about how many different compression algorithms that might have originally been developed for wireless technologies, right? Because that was the problem, right? When mobiles came out, right, everybody needed to have better ways to do this. We started putting it into the data space, and even before the pandemic, the slide share applications on the internet were, it was like, and that was something that's just your slides, right? It wasn't live video coverage. But how is it that we get to that point, or how is it that we can watch live sports, that's halfway across the world, that's being broadcast in these ways? And it has to do with data compression, both the availability of the network, but also the dreamy, cool tech that's behind making that possible. But it's also about having established that, I suppose, that there was capability both at the fiber level and at the data packaging level, and that you could start thinking about what would be a dream application on top of that. But it's about taking a platform and thinking about possibilities, and that gets into the philosophical thing about thinking about how information can be used. I think we've barely scratched the surface. So the reason quantum compute has started talking about its impact on materials is because quantum computers are effectively quantum materials, right? So they're very good at emulating and solving problems about other quantum materials. And I mean, it is abstraction, right? But I think that this is something that will have impact on the world in ways that it's true. We don't know what that means right now.
Well, what would you think? I mean, what would a quantum network actually connect? What would be your, like, if we were to go 20 years, 10 years, 15 years down the road and look at what kind of assumptions did we not see? What would they miss out on? What was our misconceptions? What would a mature quantum network actually connect?
Well, I think that the application that would be the 10 to 20-year timeline, which will be meaningful to everyone, is quantum data centers. So that right now, when people talk about quantum computers, they talk about different types of physical modalities being better for different types of problem solving. But imagine you have this sort of data center that has many different types of quantum computers in it, which is able to route information for different subsets of the problem to the right types of computers in order to do something. That type of computational power has never been dreamed about. It's one thing to do things quickly. It's another thing to be able to solve problems at a very deep level of modeling that we've never been able to attempt. So much of the electronics, semiconductors, etc., and photonics that we use, those are actually enabled by quantum phenomena, since quantum is essentially the science of the very small. And it's those types of things that happen at the nanoscale that create a lot of the electronics we take for granted now, and all of the components within it. Who knows what that's going to mean in the future? I would be willing to bet that the semiconductor industry, et cetera, is going to benefit tremendously from the abilities to do new material design, and that's the one that impacts all of us, right? Our world lives off of that. So I would be putting my money there. Drugs, I mean, so my sentiments on drug development are always that there's lots of beautiful ways to predict a lot of target candidates. The proof is in being able to test them in a population through clinical trials, et cetera. So just because you come up with a lot of really great candidates, and I think that that's a useful exercise, there's still a very long testing back end to drug development. Whereas with materials, again, you can create a lot of candidate types and test them out and make progress, I think, differently in that space. So anyway, we'll see.
One couldn't argue that we can hack chemistry and biology. We'd understand cells and neurons and everything. We
Yeah.
understand the body. We can have, we don't have to test it because we would know it, right? That would be one argument. But I think it's very exciting, and it's I mean, I'm listening to you. It's just thought through. It's just deep science on top of sitting running a company, and I mean, I love this conversation, and I've learned so much tonight.
Thank you so much
thank
for the opportunity. Yeah, this has
you.
been great.
So I would just be curious now, just for people that is not aware of Qunnect and all of your roadmap. You told me before we started, jumped into it, that you're just raising money for a Series B, and you have a roadmap that you go. Where can we read up? Where can we find the latest breakthroughs and things that you're working on? What is the roadmap for 2026? Some insights that we wanna the people could be curious about, and also where can we find information about your journey and Qunnect?
Thanks so much for the opportunity to be on the podcast. It's been really great. So the easiest place to find the most recent announcements in Qunnect is to follow us on LinkedIn. And I suppose that plays to the marketing discussion that we had earlier. That is how
Yes.
so much stuff is disseminated these days. Qunnect has a number of great announcements that have come there. So if you look at our posts, you can certainly see a lot of the exciting stuff that we've done with some of our design partners, and the links to the deeper information and papers and stuff behind those. The company is raising a Series B round right now because we have grown the company in the past few years from 3 people to 26. And if you think of everything that we've done during this time, it seems crazy that it happened with such a small team committed to doing all of these great things. That includes our manufacturing team, our install teams, et cetera, right? So everybody wears a lot of hats. So we've been exceptionally lean, but it has to do with having wildly talented innovators who are driven by the excitement to do things that haven't been done before. Right? There's something really great about seeing stuff go from dream to install, right? It's a really great path. The company itself is, again, we're in Brooklyn, New York. That's where our headquarters are. We've expanded now to a second office in Albuquerque, New Mexico. Our interest in New Mexico is that the state has committed to growing their quantum ecosystem. It has a few national labs that have contributed to the story of quantum networking through the years, and that's sort of a natural place for us to want to also hub ourselves. So we'll be growing out that office in the years to come. And then on top of that, we have a small entity also in the Netherlands that is in the House of Quantum in Delft, which is a quantum co-working space in the Netherlands. So with those 3 locations, we're obviously spread for the small team that we are, but it's our sort of journey as a company started off as being university spin out, and then growing it into a few fast and dirty prototypes that ended up eventually becoming products, and now actually expanding into being a company that manufactures and installs and supports these products and works with several of these Fortune 100 companies we were talking about before, in government and defense contractors. So our journey has been like an exciting exponential climb to try to get all of these things out the door and to support them and to start turning what we saw as a company that we didn't know was even going to survive the first 3-year lease we signed on a place, right? And now looking at it as a long-term possibility of we've now deployed quantum hardware that works, and we're working with these real hyperscalers, right, and serious entities in order to actually see how these things are going to create the future for everyone else. So each one of our steps has been very deliberate. That's what you can see on the posts. Yes, is the language a little hypey and sensational? Well, yeah, we want you to be excited the way we're excited, but at the same time, it all plays off of real results. So anything that you would like to learn about Qunnect, feel free to basically ping any of us through LinkedIn, where that's our primary sort of like distribution of information.
Wonderful, Noel. I got excited from someone running Entangled Photons through Brooklyn and Queen, but I had so much in-depth learning experiences tonight. So thank you so much for coming on, and I wish you all best for the Series P and for raising the money. And I'm very excited about like the future of the quantum networking journey that you have started. And again, thank you so much for doing this.
Yeah, thank you for the opportunity to be here. It was really great to have the chance to be able to share what we've done on your podcast.